Hello everyone, I have the space today, so I'm going to take the time to finally do my videos about deriving the Euler Lagrange equations. So the Euler Lagrange equations, remember we're saying, are a consequence of having this quantity as the action, which directly takes in a trajectory over some time interval, and the action is equal to the integral over that time interval of the Lagrangian, which depends on the trajectory, the velocity, and potentially the time. So the Euler Lagrange equations then come from asking that we want to find the specific trajectory q such that the action is minimized or stationary with respect to variations of the trajectory. So this sort of stationary action, we're saying should give us the Euler Lagrange equations. Okay. So this is the sort of very informal method of doing this first part of the video. And so what we're going to do is basically look at this kind of Riemann sum form of this integral. And how exactly that works is that, we could have some trajectory, or let's call this q, t. So from A to B, so this is some arbitrary trajectory. And what a Riemann sum of this integral would look like is breaking the interval up into little discrete sort of chunks. Then, right, so let's do that. So something like this. And then at each point in time, we could then look at what is the position at those times, then create a sort of analogous plot for the Lagrangian in a way that we have to talk about a bit, and then do these sort of rectangle sums, right? And then once we've done that for some sort of finite number of chunks, we then take the limit as we increase the number of divisions we do of the time interval. So the thing is, though, that the Lagrangian doesn't just depend on the position, it also depends on the velocity. So we kind of have to figure out a way to determine what the velocity should be. Okay, I'm just going to do the rest of these for completion. Okay. So in a sort of equivalent way to doing a Riemann sum, we're going to say that the only knowledge of the trajectory that we have is through the positions of the particle at these specific points in time. So we're going to erase all these sort of in-between segments. Okay? And then for sort of each little small interval of time, so let's say that the length of each of these we call delta t, we want to find a way to approximate what the value of the Lagrangian should be based on our sort of data about the positions of the particle at each time. Then we'll multiply that by delta t instead of dt and then add them all up. And that gives us the action. Okay. So for each of these, so let's say we could have the Lagrangian at a certain time. So let's say ti. And what I mean by this is that, let's say, A we call t0. The next time we call t1, then t2, t3, t4, so on and so on, till we get till our last time, which we'll call tn, let's say. Then in the actual action integral, we take the limit as n goes to infinity. Okay, but to kind of do this for a specific, or really it might be more accurate to say that t0 is this first time interval. But it doesn't really matter that much once we take the limit to infinity. So we'll say that right, so how I should write this is Lagrangian of let's sort of informally write this as this, but what I really mean is that what we're going to plug in to our actual Lagrangian function is our sort of approximate value for the position, our approximate value for the velocity, and then whatever this time is. Okay. So let me move this back here. So this tilde here I'm using to denote the sort of averages in here. So the idea is that within this one time interval, we want to get, let's call this this. That might make things a bit more clear. We want to get a sort of idea for what the average of the Lagrangian is in this kind of interval here. And we can do that by considering what the sort of average position is and average velocity is. And then multiply that, or sorry, I'm getting ahead of myself. So consider what these average things are, and then put those into the Lagrangian, and that gives us an idea of what the Lagrangian is in this small time interval. Okay, well, this sort of q tilde, ti, well, we can think of it as a kind of average of these two positions, like a literal average. So we would have q of ti plus q of ti plus 1 divided by 2. And then for our sort of average velocity, we can use, again, not exactly that, but our familiar idea of what an average velocity is, which would be, let me write this a little further down. So q of ti plus 1 minus q of ti divided by delta t. Okay? Then we plug these into the Lagrangian, and that gives us our sort of average value for the Lagrangian in that interval. Okay? So then what the action consists of is adding up all of these things. So we'd have the Lagrangian of, so the first one, we would have qt0, which I'm going to denote as just q0, and then plus q1 over 2. And then the velocity, the average velocity, would be q1 minus q0 over delta t. And this is at t0. And if you want, you could also do the average time. I don't think it actually matters. Yeah. And then, so this is just the first part. Then we can do the next part, which would be, okay, right. So, sorry. So the first part, this interval, we then have to multiply by delta t. And then, because we're integrating this, so this is all multiplied by delta t. Then we add Lagrangian at this next average position. And then we just keep on doing this until we get to the end of our time interval. Okay. So what the point is then is that we want these Q's, this sort of almost, Susskind calls it a stroboscopic kind of idea of a particle moving. So, you know, strobe light, it only is on for like these brief flashes of time. So we're kind of recording the particle at these brief instances of time. And then for a sort of stroboscopic idea of a trajectory, how we can consider varying the trajectory so that the action is minimized is by literally varying, you know, each point here, each position here at the given times. So we need to minimize this action with respect to q0, q1, q2, q3, q4, on and on, up until qn. So this is a widely multivariable function. And so the condition that the action is stationary or minimized is that we need ds by dqi to be equal to 0 for all I in the sort of 0 through n. Okay? So what actually is this partial derivative? Well, these qi, so specific qi, factors into the action through two of these sort of Lagrangian terms, and it factors into each of the Lagrangian terms through the position and the velocity. Okay? So we can model it based off these two terms. So let's say I'm going to imagine that qi is q1, but there's nothing special about q1. We can do this for all I. So ds by dqi will be equal to, so we get this first Lagrangian term, qi affects the position, so we get dl by dq, and then dl by dq, and then the derivative of what we enter into the position with respect to qi, which would be 1/2. And then it also affects the velocity, which would be dl by dq dot, and then times 1 over delta t. Okay? And then all of this is multiplied by delta t because we have these factors. Right. And then from our second Lagrangian term, you get a 1/2 dl by dq plus dl by dq dot, and then we actually get a minus sign because the next Lagrangian term will be subtracting qi in the velocity. So minus dl by dq dot times 1 over delta t. And this is times delta t. Okay, but this is 0, right? That's our condition that the action is stationary with respect to variations of qi. So then we can actually get rid of these delta t factors. Just divide by them. Okay. Well, we can add some stuff together, right? So we get 0 equals dl by dq, and then minus maybe I should have been a little more specific. So right, this is dl by dq at this position, the first one, at this sort of average position, and this is dl by dq at this position for the second one. But in the limit, these intervals get so close to each other that there's no real distinction. Okay? So you can kind of think of this as this one is at ti minus 1, and this one is at ti. This one is at ti minus 1, and this one is at ti. I forgot to make that distinction, but it's only a little bit important because our equation now is 0 equals, so you get dl by dq here plus dl by dq here. And then because the time intervals get so close to each other in the limit that these are essentially the same things. Okay. Then here, what's happening is that if you pull out this minus sign, then what we have is dl by dq dot at ti minus dl by dq dot at ti minus 1 divided by delta t. And I know it's a bit slanted, but bear with me. if you take the limit as delta t gets very small, and these consecutive times get very, very close to each other, then what this becomes is a derivative. It's the time derivative. So we have this part first. It's the time derivative of dl by dq dot. Okay? So these equations are true at ti. The condition that the action is, so overall, the condition that the action is stationary with respect to variations of qi implied this equation at ti. And by the way, this is the Euler Lagrange equation. So then the condition that the action is stationary with respect to varying any of the positions would then give you the Euler Lagrange equation for every time ti, right? And so in the limit, every time ti just becomes all times. So what we get, once we do the full limit and all of its considerations, is that for all times t, we can write this as dl by dq is equal to d by dt of dl by dq dot. Okay. So I hope this is kind of helpful. This is not my favorite way of deriving it, but I do think it is pretty intuitive how it works out. Because all we're doing is sort of doing, the original idea of an integral, and then we're kind of doing these approximate methods, and then taking the limit and see how it works out. So it is very much in the spirit of calculus. But next we'll do something that will make a bit more sense. All right.